This is my Lab4Report circuit and the capacitor. The purpose of the lab is first examine the behavior of series circuit and measure the potential difference, and then we'll create a CCK simulation for RA circuit and observe the charging and discharging process, find the relation between voltage change and time in the discharging process. The principles used here are basically the three. First, the node rule, and then the loop rule, which is actually the energy conservation principle, and third is Ohm's law. First, we will deal with the series circuit, and first we will predict the I value. According to the node rule, the I1 will be equal to the I2. And according to the loop rule, we will generate these formula. And when we insert Ohm law here, I will get the predicted value of the R1 equal to I2 will be equal to 0.02 ampere. This is the result that when I run the simulation of the series circuit, you will find that the value on the ammeter is 0.02 ampere, exactly the same as I have predicted. And then we'll replace one ammeter with a voltmeter. For the voltmeter, it actually measures the value of the delta V R1 plus delta V R2. And the ammeter, the value of it is equal to 0. Because the circuit is not connected, there's no electrons flow through the circuit. On the upper left, you will find the potential difference in each part of the circuit, and below is the graph that I generated. You will find a drop in the point C and the point E because it has encountered the resistor. And then we will put the ammeter parallel to the 100 ohm resistor. You will find the I value increases from 0.02 ampere to 0.06 ampere. According to the node rule, the I input will be equal to the I output. There's two paths here. The first path is a resistor path of 100 ohm, and the second path is a path that passes through the ammeter, which is 0 ohm. Because almost all the current pass through the second path, we will assume that we can ignore the path of the resistor with 100 ohm. And put the Ohm law here, we'll find the I value will be equal to 0.06 ampere, which is exactly the same as the value that's shown by the ammeter. For the RC circuit, the charging process, it will experience three stages. In the first stage, when the T is equal to 0, the capacitor is uncharged. When it moves through the second stage, the current flows faster and light bulb becomes brighter. And when it moves to the third stage, when the stage that the capacitor has finally been charged, the current will flow through slower and the light bulb become dimmer. For the discharging process, that we will connect a capacitor to a 10 ohm bulb, you will find the capacitor act exactly like a battery, and it also experiences three similar stages. In the first stage, it is charged, and then it will generate the current to make the light bulb bright, and when you go through the second stage to the third stage, the light bulb will become dimmer, and finally the capacitor will be entirely discharged. This is the charging time and discharging time for the 10 ohm and 20 ohm bulb. You will find generally the discharging process takes longer time, and the bulb with a lower resistance will charge and discharge faster. At the end, we will build the relationship of the voltage and the time. First, we will measure the delta V naught before discharging, which is equal to 9 volt. And I will repeatedly pause the simulation to find the delta V for 20 seconds. You will find the values that on the right hand side is the value that I insert into the Excel. And then we'll plot the relationship between line delta V divided by delta V naught versus the time graph. Based on this graph, we will calculate the RC. This is the graph of the relationship. You will find it's a negative linear relationship. The slope will be equal to minus 0.053. And use this slope, we'll calculate the RC will be equal to 80.86. Answer for the what if question. The first question is that what if we use the actual ammeter instead of an ideal simulated ammeter? I think the real ammeter has the inner resistance and it will make the I value a little smaller. And then the question is, what if we use the real battery to charge a real capacitor with no resistor in the current? The real battery will have inner resistance, and the real capacitor will dissipate the energy through the process. So that will make the process of the capacitor charging much more slower than the ideal circumstance. Thanks for listening. That is all.